Hi, this is Norbert Herbert from Activity, and this is our new webinar for developing IoT tracking solutions with ABV Murata geolocation module. The slides and the recording will be shared after the webinar. We are going to activate the Q&A so that you can ask your question while I am talking. Then I will answer your question after the end of the webinar. Now I am going to give the floor to Suman Thapa for Murata, who is going to introduce the hardware architecture of the module.
Thanks, Norbert. My name is Suman Thapa, and I'm a product engineer for LPWA modules at Murata Electronics, and I'm based at Murata France office. The new Type 1WL is a very unique module which features multiple technologies including LoRa. It is an ideal solution for both indoor and outdoor geolocation. This module is a collaboration of ABO and Murata, bringing their respective expertise together into a single module. The 1WL module hardware is designed and manufactured by Murata, leveraging its long legacy of module development and manufacturing. The geolocation firmware and the software development kits are developed by Abiway, a market leader company in geolocation field. All of this allows for a rapid development for an IoT tracking solution. I will go into more details about the 1WL module on the next few slides. Type 1WL module from ABWay and Murata has everything you need to quickly and easily develop IoT tracker device. First, this module has STM32WB, which is a microcontroller from ST Microelectronics. It is a dual-core, low-power wireless MCU, which is based on 32-bit ARM Cortex M0 Plus and 32-bit Cortex M4 architecture. Cortex M0 Plus is a network processor and it contains integrated BLE transceiver. However, Cortex M4 is an application processor which is open for customer to write their host application. Roughly 1 megabyte of flash memory is available for the host application. Second, this module features LR1110 chipset from Semtech. More than a chipset, it is an ultra-low power platform that integrates a LoRa transceiver, multi-constellation low-power GNSS scanner, and passive Wi-Fi MAC address scanner. These features are very ideal for geolocation application. The LR1110 is designed to comply with the physical layer requirement of LoRaWAN specification released by LoRa Alliance. Besides, this device features a very low power multi-band front end which can acquire Wi-Fi access point MAC addresses and GNSS satellite signals. To calculate the position of an object, these signals need to be transmitted to a cloud-based geolocation server. The signal transmission to geolocation server can be done through LoRaWAN. Since all the calculation is done on the server side, this feature enables a unique balance between low power and performance. Third, the module also offers a hardware-based GNSS chipset, but it is totally optional. This hardware is for those who wants to have a standalone GNSS feature without the need of cloud-based server. Moreover, adding this chipset can also help to enhance the geolocation accuracy. It is totally up to the customer if they need this hardware chipset or not. Similarly, there is also another optional chipset, hardware secure element to store device keys securely. It is for those who wants to have extra layer of security in their devices. And as an option, secure element can be personalized and pre-provisioned on the ThinkPark activation platform. But if you think your device is already secure enough or have software-based solution to achieve security, then this chipset becomes totally redundant. Again, it is totally up to the customer if they need this hardware chipset or not. I will highlight additional features on my next slide. The size of the 1WL is roughly 17 by 17 by 2 millimeter, which is basically the size of a 2032 coin cell battery. Thanks to the optimized hardware and software design, this module has ultra low power consumption, which will greatly extend the battery life of the module. There are several input-output interfaces available in this module. including the likes of GPIOs, ADC, I2C, SPI, UART, USB. Roughly 1 megabyte of flash memory is available in this module, which is dedicated for customer to write their host application. In a nutshell, neither customer need to have their own host processor nor need to purchase any external MCU. They can fully use the flash memory that comes integrated in this module. By default, this module comes FCC IC CE regulatory certified. Additionally, we will also do LoRaWAN and BLE pre-certification. This module offers a single hardware solution for those who wants to embed both indoor and outdoor geolocalization features together. So, what are the value propositions of this module? Thanks to our compact design, this module already includes all the necessary components that are required to make a multi-technology tracker devices. With this modular approach, not only the fewer number of components will be needed on the final PCB, but the number of PCB layers that is required will also decrease. Hence, Type 1WL module will greatly simplify the PCB design, optimizes the bill of materials, and reduces the negotiation needed with various component suppliers. In Murata, our modules go through several mechanical and reliability tests, including the likes of soldering, EST, temperature test, drop test, and many more. This is to ensure that we deliver high quality and best in class product. Since Murata already do these tests, customer don't need to worry so much on product testing, and they can have peace of mind while developing their end devices. Moreover, the module RF certification can be reused, and possibly no regulatory certification is required depending on where the module is used in the world. This will result in reduced engineering cost and effort. We will provide design guides. All you have to do is simply follow the design guide instruction. Also, evaluation board is already made available. This can be used for performance evaluation of the module and also for testing user application. No need to start prototyping your design from the day one. You can play with the evaluation board until you are fully convinced to select this module in your bill of materials. Furthermore, ABWay has developed software development kits exclusively for this module. First release has already been done and is available through ABWay GitHub page. This SDK will be very crucial to reduce time to market. In more detail, SDK will be highlighted later by Norbert from Actility. One WL module comes in three different flavor depending on the chipset available in it. Starting from the first row of this table, the first variant is named as Type 1WL with 857 as a 3-digit termination. Full manufacturing part number starts from LBE. This version of the module variant will have STM32WB and LR1110 chipsets, which will feature LoRa, BLE, Wi-Fi sniffing, and low-powered GNSS. Second one is named as Type 1WL633. This module includes all the chipsets available in the previous version, plus MT3333 GNSS chipset from MediaTek. The features are LoRa, BLE, Wi-Fi sniffing, low-powered GNSS, and multi-constellation GNSS. Last one, we have Type 1WL042, and compared to our second variant, it additionally has TO136. This is hardware secure element from our partner company called Trusted Object. However, if you don't want a hardware secure element but still want equivalent level of security through other means, then the same company can provide software-based secure element also. Please visit Trusted Object's website or contact their local sales for more information. And what I would like to highlight here is that regardless of the different hardware offering, all the module variants will have the same module footprint. The compact size, ultra low power consumption, fully integrated application processor, software development kit from ABY, regulatory certification, and quick time to market make this module a fit for almost any of geolocation application. Here are a few key applications that we see as an extremely good fit for the module. Supply chain monitoring, tools monitoring, shared scooter tracking, parking policy enforcement, cattle pet tracking, social distancing, geofencing, child elderly safety and protection. What I want to emphasize is that these are just some of the applications for the module from the geolocation vertical. In reality, it can be used almost for any wireless IoT application that needs low power, wide area connectivity. Many people are asking where will be the module samples available. To answer this question, ThinkPark Market by Actility and Murata Distribution Partners will be your go-to place for purchasing module and the evaluation kit. Today, the module samples and the evaluation kits are already available in ThinkPark Market. You can order them from the link available in this slide or simply visit ThinkPark Market website. Moreover, you can also reach out to either Actility or ABY local sales. They will be ready there to deliver you the product right away. Later in Q1 2023, modules will be available through some of the Murata multinational distribution partner. For more information, please contact your Murata local sales. At this point, I would like to hand the control over to Norbert from Actility.
Thank you, Suman. It was really a great introduction to our new Type 1WL module. In the second part of this webinar, I will explain how it can be used for building RTLS solutions. What we have already learned is that we have got a geolocation module that is a compact circuit component with ultra low power consumption, and it includes everything that a tracker device needs: a microcontroller, a LoRa chip, and a GNSS chip. So what kind of tracker devices can we build from this module? The best examples are the existing tracker portfolio of ABWay. Let's have a quick look at the trackers developed by ABWay. These are the industrial tracker and the compact tracker, the micro tracker and the smart badge. These devices don't utilize the module yet, but we are currently in the process of redesigning their PCB to use the module. All these devices have a very similar hardware design: low power MCU, GNSS module, LoRaWAN modem, accelerometer, and they all support indoor-outdoor geolocation. They are really good examples of trackers that can be built from our module. We have developed an advanced firmware for these devices that support multi-technology geolocalization. The supported technologies are GPS, low power GPS, BLE scanning, Wi-Fi scanning, and Kupa beaconing. The firmware supports several tracking operation modes like permanent tracking, motion tracking, start and of movement tracking, BLE zoning, and geofencing. And the firmware has several non-tracking operation modes like activity monitoring, shock detection, SOS operation mode, scan collection, and many more. This firmware is not ported to the new module yet, but we have a strict development roadmap to do the porting as soon as possible. ABWay and Actility have several years of experience with developing, consulting, and selling low-power geolocation solutions. While ABWay created several different types of tracker devices, Actility developed its own low-power connectivity infrastructure called ThinkPark. This immediately answers our next questions. How can we connect the devices to the backend, and how can application servers receive location updates? This is explained on our next slide. In an outdoor environment, devices are listening to the signals broadcasted by the satellites, and then the device processes that data, calculates its own position, its own coordinates, and sends that data through a LoRaWAN network to a central application server. However, in an indoor environment, the devices cannot receive any signal from the satellites. In that case, the devices will scan for local radio sources like BLE beacons or Wi-Fi routers. So let me show you a BLE beacon. this is how it looks like. These are small devices that could be put on the wall in an indoor environment. They are battery-powered devices, and the battery could last several years. So the result of the scan will be sent through a LoRaWAN network to a central application server. But in that case, the application server will not receive exact coordinates. The application server will only receive a list of BLE beacon IDs or Wi-Fi SSIDs, and it will be the task of the application server to calculate or estimate the location of the end device. Actility has developed a cloud service to resolve a list of BLE beacon IDs or Wi-Fi SSIDs reported by your trackers to real coordinates. The heart of that service is our location solver called ThinkPackX Location Engine. It receives data from the network server and forwards the resolved locations to the application server. We have a large customer base, and I am personally having meetings with clients and prospects every day. Why am I saying that as an introduction of the SDK of our new geolocation module? Because we have designed the module and its SDK based on all information we collected from our partners on these meetings. What were these? We learned that almost all our SI partners have got their own unique use case, and it is almost impossible to develop a unified firmware that fulfills the requirements of all use cases. We also learned that many systems integrators would be ready to invest time and effort in developing customized applications and firmware if they found a flexible hardware with a good documentation and good development kit. We started discussing the possibilities of selling only the PCBs of our existing trackers and let our partners develop their firmware on that hardware. However, our board was designed to be used by our experienced developers, and it is not so easy to be used by third parties. It would have required a lot of support resources from our side to help such development on our legacy PCBs. The solution we found to fulfill this market requirement was a new module with a well-prepared SDK. So how can we help the development effort of our partners? The ABW Murata Evaluation Board has been designed as a complete demonstration and development platform for the ABW Murata geolocation module. The evaluation board can be considered as a reference design for application development. The board includes the following components: the module itself with embedded microcontroller and GNSS and LoRaWAN chip, a power supply including a battery charger, an ST-Link debugger, and this onboard ST-Link debugger makes the developer's life very convenient because they don't need to use an external debugger like this one. However, if they still want to use their own external debugger, then they can connect that debugger to the board through this JTAG interface. The board has a UART over USB connector to connect external systems to the GNSS chip or to the MCU. And the board has a dedicated USB port that could be used by your application. There are debug LEDs, debug buttons, and a buzzer that helps you to test your application. And there are two sensors, a pressure sensor and an accelerometer. Both are connected to the MCU through an I2C interface. The board has an external flash memory that is connected to the MCU through an SPI interface. And the board has three antennas: a GNSS antenna, a LoRa antenna, and a shared 2.4 GHz antenna for Wi-Fi PLE scanning. And the board is delivered with an Eclipse-based integrated development environment called STM32Cube IDE, with drivers to help integration with onboard peripherals and example IoT applications running on FreeRTOS. All these software components are published in a dedicated GitHub repository under the ABW account. This is how the Eclipse-based STM32Cube IDE looks like. And these are the drivers published in our GitHub repository. These are the FreeRTOS kernel, STM32 hardware abstraction layer, the BLE drivers, the USB drivers, LoRaWAN MAC protocol stack, LR11 and 10 drivers, and many more. Let's have a closer look at the directory structure of our GitHub repository. Our quick start guide is in the README file. The AOS SDK folder includes all our precompiled drivers and header files. AOS stands for ABW Operating System. And then we have the apps folder that includes open source demo applications that are organized in two subfolders. The first subfolder is the ABW folder that includes applications delivered by the ABW R&D team. There is currently only one application in this folder, the CLI application that allows users to test all features of the module through a command line interface. The second folder is the community folder for applications that are developed by our community members. We would like to encourage all developers to fork our repository, add their own demo applications, and create new pull requests so that their app would be published in this repository. Now let's continue with a quick application development demo. First, we need to visit the GitHub repository and read the README file that is actually a quick start guide. It explains how to clone the repository, how to install the IDE, and how to compile the code and download it into the module. I have already cloned the repository. I took the reference from here and cloned the repository, and after that I opened the project in my IDE. And now I select the main.c file and use the hammer icon to compile the code. So I click on it and wait until the code will be compiled. Yes, now it's finished. The next step is that I take the board and connect the board to my computer through a USB cable. Yes, the LED is here lighting, so the board is connected. And then the next step is that I download the code to the device. I click on this triangle, green triangle here, this icon, and the result will be that the IDE will connect to the ST-Link debugger, and through the debugger it will flash my device. So let's wait for a few more seconds. Now, download in progress, shutting down, exit, and now my device is rebooted. And just look in the main.c file, there is this Node snippet here that is making the LED blink. And let's check that the LED, the debug LED is blinking or not. And you can see that the debug LED is indeed blinking. And now we can use PuTTY to set up a serial line connection to the device and log in to the command line interface. The password is 456. This is described in the README file. And now I am logged in as a super user. I can use the help command to list all the commands that are supported here. So I can use the BLE command to configure Bluetooth, the GNSS command to configure the GNSS, GPIO, many other commands are available here. Mainly the commands are, the name of the commands are self-explanatory, but you can always use the help. So for example, let's use Wi-Fi. And then I get further information what kind of subcommands I can use together with Wi-Fi. For example, Wi-Fi scan. Let's wait for a few moments. And now the device was scanning for Wi-Fi routers in my neighborhood, and 5 Wi-Fi routers have been found, and the associated signal strength is also reported. So all information is here. Let's use help again. And then settings is also an important command. Settings. And I can combine it with display. So settings, display, and it shows the current configuration, the provisioning of the device. So it has been personalized for the EU 868 MHz RF region for over-the-air activation with this dev UI and with this join EUI. And also the network key and the app key has been specified, but it's not shown because it's secret. So the way you set any parameter is settings, set, and then these are the options. For example, you can change the app key if you want. Settings, set, app key, and then I can put the app key. And after enter, the app key would be set. I don't want to do that. I have already done it. And based on that parameter, I have already provisioned my device on the ThinkPark Enterprise Community console. So let's go there. This is the console, the dashboard of the console. Let me list my devices. And here are all my devices under this account. And this is the ABV module, what I have already provisioned here. And let's scroll down and look for the message logs. So these are the message logs, and what you can see here that the last message what was sent by this device has the frame counter value of 42. So I can send another uplink message just by pushing the button on the device. So I push the button, but I think it makes sense to see the console in parallel. So let me switch to the PuTTY console. Where I can see, okay, here is the console. So now if I push the button, what will happen? You see that an uplink message has been sent and it's shown on the console of the CLI interface. And if I go back to the console of the network server, I refresh the screen and I see that the latest uplink message fcount number was 42 and now it is 43, and there was a downlink message sent as a reply. So there is a more detailed view here, and I can check what uplink message, what was the content of the uplink message. If I go here and here I can see that the content was AABB and CC. How can I check whether that was really the message what was sent by the device? I just need to switch back to the IDE here. And if I check the main.c file, what is supposed to be happen upon pressing the button. So here is the GPIO configuration part. And there is a callback function, and this is a callback function, the on button press callback function. And inside that function, what I can see that there is an array. This is called message payload or payload, and AABB and CC is the content of the array, what is sent with this function here. So indeed, if I push the button, the device will send an uplink message. I cannot do a very detailed programming training here. I just wanted to give you a teaser about how easy to use this IDE and what nice applications you can develop using this Service Development Kit.
Okay. Now I am opening the Q&A session. So let's look at the questions, and I am doing my best to answer them. So let's have a look at the questions. We already received 3 questions. So let's go through. Might your solution be used with set of existing BLE beacons or Wi-Fi hotspots? Yes, Zoltán was asking this question. you don't need to install new Wi-Fi routers if you already have them in your neighborhood. Regarding BLE beacons, you need to register those BLE beacons in our location solver. So if you already have BLE beacons, you need to let our location solver first know where those BLE beacons are located and what their beacon ID is, and then our location solver can use them as reference to calculate the location. There was another question earlier, I remember. No more question. Okay. What is the main difference between the module and the architecture of our existing devices? So the architecture is the same. The difference is that the module is a compact circuit component that you can easily put on a new PCB, while the architecture of the existing devices is based on a PCB. So all these components, the GNSS chip, the MCU, and the LoRa chip, are directly soldered on the PCB, and the existing devices doesn't use the LR11 and 10, the new chip from Semtech. The question about certification, whether the module will be certified. Of course, this is one of the main advantages of using this module, because if you are using this module, your device will be automatically certified. So since we very soon are going to collect all certifications for the most important regions, for the US 915 region, for ES 923 region, and EU 868 megahertz region. So once we get all these certifications, any device you build based on this module will be certified automatically if you use the same LoRa protocol stack. Whether low power requirements already taken into account in our SDK? Yes. Our SDK, all the drivers are using the MCU in low power mode. So what would be the benefit? Okay, so the end users will not have any benefit if we change the architecture of the current smart badge so that it is using the module. The main benefit will be that the manufacturing cost from activity side would be lower, and anyone who would use this module for building their own trackers would face lower manufacturing costs and simpler circuit design. So whether the module can be used for any other application than geolocation and tracking, the answer is yes, because this module includes an MCU and a LoRa chip, and any LoRaWAN device that requires an MCU and the LoRaWAN chip could be built from this module. You can use the GPIO ports of the module. So, for example, you can build a panic button device, or any kind of, or even a pulse counter to collect data from pulses from water meters. So many applications could be supported by that module. However, since the module includes additional components that may not be needed for your application, its price could be a bit higher in that case if you wouldn't use it for geolocation.
So there is still one question, which is, can I use Visual Code as ID? I will let you take this question.
Yes. You can use any IDE as you want. Even the text editor could be used. But the STM32 Cube IDE has lots of benefits, and we encourage all the developers to use that. And all our code on GitHub are for this IDE, because if you use that, that is integrated with the onboard ST-Link debugger. And you just need to click on the downlink icon of the debugger, and then it will automatically compile the code with the right toolchain and flash the code into the device. So what is the list price for the Type 1 WL module alone? I cannot say it because after signing an NDA, we can share our pricing. Please contact our sales team, and our sales team will provide you this information.
I hope you have found this session very insightful. And if you have any more inquiries, please feel free to reach out to local sales from Murata, Abiway, or Actility. You can reach out to anyone from these three companies. We will be there to support you, your geolocation journey, or if you have any other, please feel free to reach out to us. Thank you.
So thank you very much for your attention, and don't hesitate to contact us if you have further questions.